This is a quick walkthrough of the SC18 poster contribution applying the execution cache memory performance model, current state of practice. The poster is organized in the following way. All the orange boxes describe the theory of the model and how it is constructed using simple examples. The blue boxes demonstrate the model using more complicated case studies, and the green bubbles give more information or describe open questions. So the first step in constructing the model is an assessment of cache architectures and transfer times. We need to get hold of information regarding the maximum possible bandwidth between adjacent cache levels and the speed of data transfer between those. For example, BL1, L2 is the theoretical bandwidth between the L2 and L1 cache of this particular process architecture. Most of these data are actually documented by vendors. Some have to be measured using micro benchmarks, such as the memory bandwidth. Once we have these numbers, we can calculate so-called optimistic transfer times by dividing the data volume that's transferred through the cache hierarchy levels by the respective bandwidths. The data volumes have to be derived by code analysis. So we have to have an interaction model of the code and the hardware that tells us how many bytes have to be transferred in order to do whatever has to be done in terms of work in the core. This ratio, volume divided by bandwidth, is a time, and this time we assume is the transfer time of the data between two adjacent cache or memory hierarchy levels. We totally ignore any latency contributions here. Usually we calculate these numbers for a certain number of iterations, for example 8, but we also could choose one iteration as a baseline. It doesn't really matter as long as we stay consistent. Here we demonstrate how this is done using the stream triad loop, A equals B plus scalar times C. This is a pure streaming kernel, which means all the data volumes through adjacent cache levels are the same through the complete memory hierarchy. Per iteration, the code transfers 32 bytes. And if we take on this short notation that we devised, we can say that, for example, transferring the data between L1 and L2 cache takes 4 cycles, transferring data between L2 and L3 caches takes 8 cycles, and transferring the data between memory and L3 and back takes 18.4 cycles. In this case, we have chosen 8 iterations as the execution baseline. In order to help with this kind of analysis, which is usually done with pen and paper in simple situations, we could employ tools such as PyCacheSim or Kerncraft, which are tools that are able to construct this kind of analysis in simple cases just by looking at the source code. For validation of the model, we could employ different tools, for example, Liquid Perf Counter for measuring the data volume through the cache hierarchy, PAPI, or Linux Perf. The second component of the model is the in-core execution. Here we look at the code of the loop, either at the assembly code or the high-level code, and we try to come up with 2 possible predictions. The first prediction is the optimistic one. It's a best case or maximum throughput prediction. We take all the instructions that the loop is comprised of, and we calculate which pipeline takes the longest time to complete them. In this particular case, we have 2 load instructions, 1 store, 3 add instructions, and 1 multiply. So it takes 3 cycles to execute all the adds, which means the add is the bottleneck in our particular case here. This throughput prediction is then split in 2 different contributions, a so-called non-overlapping and an overlapping time. The difference is that T non-overlapping, TNOL, interacts with the cache hierarchy, while TOL does not. In practice, this means on Intel processors that in each cycle in which a load is retired in the core, nothing can be transferred between the L1 and the L2 cache. We'll come to that later. The other prediction that we can come up with is the so-called critical path analysis. Here we regard the actual dependencies between different instructions in the loop. Taking all the latencies into account, we construct a critical path through the code and come up with a worst-case prediction for the execution. Once the data is in the L1 cache, this is the slowest that we can measure for this loop. Whether or not successive iterations of the loop can overlap remains to be seen. We call this critical path prediction TCP. Here we have an example of a 5-point stencil on a Xeon Skylake with AVX 512 instructions, where the throughput analysis tells us we have 4 instructions in terms of loads. We have 1 store, 3 adds, and 1 multiply. The group of instructions that takes the longest to execute is the load. So here we need 2 cycles for the non-overlapping part. The overlapping part, which comprises all the other instructions, takes 1.5 cycles at least. So that would give us 1.5 cycles for the overlapping part. However, executing 9 microops in 2 cycles is a little too much for this architecture, and we have to add another quarter cycle to account for that, for the overlapping part. The critical path analysis in this case tells us that 15 cycles are needed to actually execute the loop body. In practice, this is probably not observed because successive iterations can overlap. Here also we have the option to employ analysis tools to help with the analysis. That is also usually done with pen and paper. There's the Intel Architecture Code Analyzer, a closed source tool from Intel, or the open source architecture code analyzer Osaka, developed by the Wellein group. Also Kerncraft employs Ayaka to come up with this kind of analysis. So once we have constructed the data transfer and in-core execution times, we can put the model together. And this is where we employ an actual machine model that has to be redone for every new architecture. And the assumptions that go into this model are called overlap assumptions. Now, first we introduce a notation for the model contributions. Here we see, for example, that the overlapping part takes 7 cycles per 8 iterations. The non-overlapping part takes 2 cycles, so the 2 numbers to the left and the right of the double bar, that's the in-core prediction. And the remaining contributions are as shown. L1, L2 transfers take 4 cycles, L2, L3 transfers take 8 cycles, and L3 memory transfers take 18.4 cycles per 8 iterations. Now the art is to put these contributions together to get an actual runtime prediction. Now the most pessimistic assumption of putting together these contributions is the no overlap assumption, which means that the prediction of execution time is the maximum of the overlapping time, TOL, and the sum of all data transfer contributions. This means that whenever a data transfer occurs in the cache hierarchy between adjacent memory hierarchy levels, nothing else happens in the complete remaining memory hierarchy. With one exception, and this is the overlapping execution, which is independent and can overlap in any way it likes. It turns out that for Intel processors up to Broadwell and Skylake at least, this is a very good model that results in very accurate predictions. Now, of course, other processors could show different behavior, and for example, we could have a full overlap of data-related contributions. So if the execution time is the maximum of all individual contributions, this means that whichever takes the longest in the whole collection of data transfer times, this is what determines the runtime of the loop. So that's a fully optimistic model. We call it a light speed model. It looks like the roofline model, which also assumes a single bottleneck. However, it's not the same as roofline, because roofline is not based on theoretical transfer bandwidths, but it's based on measured bandwidth numbers, for example, between L2 cache and registers, L3 cache and registers, and so on. And then, of course, it could get complicated. We could have a partial overlap of data-related contributions. So in this case, shown here, we have a non-overlap between the register transfers, the loads, and the L1, L2 transfers, and the rest of the memory hierarchy is overlapping. Okay, so once we've got this in place, we have a notation for model predictions. For example, if the data that the benchmark needs to run is in memory, we call the prediction TECMM for an in-memory data set. And this is the rightmost entry in this notation here. If the data is in the L3 cache, we call it TECML3 and so on. So this is a notation that tells us how many cycles the loop takes to execute with the working set residing in different memory hierarchy levels. Now, as an example, we show here the AVX double precision sum reduction with a single accumulator on a Broadwell EP core with 2.3 GHz. So this is the code. A naive compiler may vectorize the code, introducing 4 accumulators in the SIMD register, but it may not unroll the code on top of that, which means we have to endure the 3-cycle latency for every single accumulation here. This gives us the following prediction. For the overlapping part, we need 6 cycles because we need 2 adds to traverse a complete cache line of 8 elements. Each add takes 3 cycles, so that leaves us with 6 for the 2 adds. And then we need 1 cycle for the loads in the kernel, 1 cycle to transfer the data from L1 to L2, 2 cycles from L3, and 4.6 cycles from memory. The prediction, assuming the non-overlapping model for Intel CPUs, gives us 6, 6, 6, and 7.6 cycles per iteration, which means that this code will perform the same no matter whether the data is in L1 cache, L2 cache, or L3 cache. If the data is in memory, we have a performance drop. This is what the model predicts in this particular case. Now, the last thing about model construction we need to look at is multicore scaling and saturation. Now, the ECM model in its plain form assumes a very simple behavior. Performance is assumed to be linear until a bandwidth bottleneck is saturated. Usually the bandwidth bottleneck on Intel CPUs, for example, is the memory interface. So the memory transfer time is the lower limit for the loop execution in the saturated case, which means that the ECM model prediction on n cores is the maximum of 1/n of the prediction of a single core and the TL3 mem transfer time. This is actually the connection between the roofline model and the ECM model, because it tells us that the loop cannot run faster than the limit given by the memory transfer time. It's also very easy then to come up with a prediction of the number of cores that are needed for saturation. The number of cores needed for saturation is the ratio of the ECM model prediction for data in memory and the time it takes to transfer the data between L3 and memory and back. So for the AVX double precision sum reduction from above, we have an ECM model of 6, 6, 6, and 7.6 cycles per 8 iterations, and the predicted saturation point is 7.6 cycles, that's the runtime prediction for data in memory, divided by 4.6 cycles, which is the time it takes to transfer the data from memory, which gives us a prediction of 2 cores needed to saturate the memory bus. This was a quick walkthrough of the theory. Now we come to application cases, and we've chosen 3 application cases here that show that the ECM model is not only good for simple streaming codes, but also for more complicated situations. Here we have a complex stencil from a code solving Maxwell equations. The code is vectorized using AVX2 via C intrinsics, and we have complex number arithmetic in this kernel. You see there's a lot of arithmetic going on here with lots of array accesses. If we employ the ECM model as shown above, then we have to look at 2 situations here. One is a situation where the layer condition is fulfilled in the L3 cache. Here we have a code balance in main memory of 112 bytes per lap, and an in-memory runtime prediction per 4 iterations of just above 80 cycles per 4 iterations. On the other hand, if the layer condition is broken, the code balance in memory goes up to 144 bytes per lap, and the prediction of the ECM model goes up to about 91 cycles. The red line shows the ECM prediction, and the blue line shows the measurement, and it's in very good agreement. The error is typically below 5%. In this case, the analysis also tells us that there's only a limited benefit from spatial blocking, because spatial blocking would only get us from 144 bytes per lap down to 112 bytes per lap, which predicts a performance improvement that may not be worth the effort. We can validate the model by measuring the data traffic through the cache hierarchy. Here in this lower graph, we see the data traffic between L1 and L2 cache, L2 and L3 cache, and L3 cache and memory, together with the respective predictions from the model, and we see also that the predictions of the data volumes are within 5% of the measurement. Our second case study is a kernel from the Blue Brain project. Here the scientific question is, what's the computational cost of a synapse? This code was vectorized with SC18 instructions by the compiler. And we see here several difficulties with this code. First of all, we have indirect data accesses in two places. We have an exponential function and 3 divides in this kernel. So it's a complex code that even comprises a function call to the exponential function. Fortunately, most of the data accesses are streaming. The indirect data accesses are benign, and we can model them by putting in knowledge about the behavior of the index field. So in essence, they don't really disturb the streaming nature of the code. Here we compare two different systems, an Intel Ivy Bridge and Intel Haswell CPU core. And we construct the model using the throughput assumption as shown above and the critical path assumption in both cases and for both architectures. Now it turns out that the throughput assumption for the Ivy Bridge processor is 34 cycles per iteration, and it means in this case that the kernel is data bound, because the overlapping part is 32.5 and the data part is 34 cycles. So this means that in this case the kernel is data bound. The ECM model prediction for the Haswell is 38.9 cycles per iteration, also data bound. For the critical path, we have a prediction of 49 cycles for the Ivy Bridge and 50 cycles per iteration for the Haswell. Now we have these predictions, and if you measure the time, we have a very interesting result. On the Ivy Bridge, the measured execution time is 48.7 cycles per iteration, which is very close to the critical path assumption. While for the Haswell, the measured execution time is 39.4 cycles per iteration, which is very close to the throughput assumption. And now this leaves us with a conclusion that the Ivy Bridge is limited by the critical path in the kernel, whereas the Haswell is limited by data transfers, most probably because of the more advanced out-of-order processing capabilities of this core. In practice, if we execute this code in a parallel way, it doesn't really matter, because on both CPUs, the ECM model predicts that it will saturate at between 3 and 5 cores. So if saturation sets in, then we don't really care whether the bottleneck on the single core is critical path or throughput. The second example from the Blue Brain kernels is the so-called sodium ion channel. Here we have an abundance of exponential functions and a lot of divides dominating the execution time, so we can expect that the overlapping part is very large, and actually it is. We have 140 cycles for the overlapping part, the full throughput overlap assumption, which means that looking at the data transfer of 28 cycles, the TECM memory execution time is surely equal or above 140 cycles. The measurement is 191 cycles, which means that the critical path at least plays a certain, albeit limited, role in this execution. From this measurement and the data prediction, we can derive that this kernel will saturate at 16 cores. So unless our CPU has 16 cores or more per CC_NUMA domain, this code appears to be scalable. Our next example is a conjugate gradient solver, which comprises 6 loops instead of just 1. Each of these loops can be modeled using the strategies outlined above. So we have the ECM model for each ECM model input for each of these loops. We have the prediction with data and memory for 8 iterations shown in this column. We have a prediction for the saturation point, it's always between 2 and 3 cores, and we have a prediction for the full domain in cycles per 8 iteration. Now, since all these loops are very much data bound, it's only natural that the full domain limit is always equal to the data transfer time between L3 cache and main memory. This is like a bandwidth bound roofline prediction. However, the single core prediction is the sum of all the ECM model predictions of all the loops, and this amounts to 152 cycles per 8 iterations, where the full domain limit is 81.3 cycles per 8 iterations. Now the measurement, which is the blue data in this graph, shows that on the single core, the prediction is within 5% of the measurement, and the saturated performance prediction is within 0.5% of the measurement, which means the model is very successful in describing the performance property of this conjugate gradient solver, even though we have 6 loops instead of just 1. Now finally, we have to look at some of the problems and open questions. One problem is saturation. It turns out that the plain ECM model saturation assumption, assuming that the scalability is perfect until a bandwidth bottleneck is hit, is a little too optimistic in many cases. Recent work shows that we can correct for that by introducing a so-called adaptive latency penalty, which assumes that the more the memory interface is utilized at a certain number of cores, the longer it takes to get some cache line from memory to the L3 cache. If we account for that in the model prediction, we can get a very good agreement between the model and the measurement, shown here by the open circles, which is the model, and the black dots, which is the measurement. The ECM model with the naive saturation assumption is shown by the dashed line here. Details of this analysis can be found in our ISC 2018 paper. One problem with the ECM model is that it assumes very strongly that the kernel we analyze is in a so-called steady state. We assume there are no startup and no wind down effects. All latencies have passed, and we basically assume that all loops are infinitely long. If this is not the case, the ECM model is bound to be much too optimistic. The second problem with the ECM model and also similar model is that irregular data accesses can only be handled by a best-worst case analysis. So if we have an axis like this, A of index of I, in the best case we can assume that we have some kind of regular structure or even stride 1 axis, which means we have a streaming kernel, which makes things very simple. In the worst case, we must assume that the index is random, and then we can introduce a latency penalty per access, but your mileage may vary with this. So it's not really part of the model to handle this kind of cases. Finally, we've pretty much shown application case studies for Intel processors where the non-overlap assumption is accurate in most cases. However, other processor architectures show different behavior. For example, the IBM Power 8 processor shows overlap at the L1 cache, while the data transfers between L2, L3, L2 memory, and L3 memory seem to line up in time. The AMD Zen or EPIC architecture seems to show full overlap, but this is preliminary data that has to be substantiated by more measurements.